Hello everybody, and welcome to our Operations Research course video lecture on chapter 17. So this is now on page 15. So note that the pages have changed a little bit since I have corrected all the, well, not all, but hopefully most horrible mistakes I made. And now we are in chapter 7, and in this chapter 7 we talk about sensitivity analysis. And this first page here in the introduction, this is more or less some general ideas what the sensitivity analysis is about or should be about, and there is not too much explicit stuff here. So this is more or less try to introduce the topic. So what are we dealing with in this course? We are dealing with LPs, linear optimization problems, and the LP can be written. We will learn this very soon. Any LP can be written in a so-called standard form, or to be completely honest, what I call a standard form. So some other people call some other forms standard forms. So for me, a standard form is a LP that is a maximization. So it's maximized Z equals objective function C transpose X, and it's subject to constraints A times X is less than equal to B. So in the standard form, they are always upper bounds, and then we always have a sign constraints. X's are non-negative. All right. Now we can think of this LP problem, maximization problem, as a function of its arguments. And now we are not thinking about x's. X's are just actually part of the solution. So this is Z star. That would be the optimal value of this. Is a Z star of C, A, and B. So C, A, and B are the parameters of the problem, but now we can think of them as an arguments of a function Z star. Okay, this function in some sense is a black box to us, at least so far, so we don't know how to calculate its value, but nevertheless GLPK will calculate it for us. So it's a function. And so as with any function, it's kind of important usually to know what happens if these parameters change, and if they change a little bit. So it's kind of how sensitive the solutions are to the parameters of the problem. And there are many reasons for this. The most obvious reason would be that this, in some sense, these parameters are quite often just estimated from somewhere. So there could be uncertainty of the actual values. Also, it could be that we want to change them a little bit, or even if we don't, they could change a little bit. So for example, if this were the more deep bakery problem, so B's are the resources, it could be that someday we get a little bit more or less of some resource. There could be changes in technology also, why not? And then the prices, okay, we can decide what the prices for the cakes are. So we might think whether we make some cake a little bit cheaper or a little bit more expensive for some reason, what happens. And well, the obvious and safe solution to this problem is then of course to solve this problem with the new parameters, but quite often we want to have at least some kind of idea what how do they change before we calculate lots of different problems for different parameters for many reasons. One reason is that it's hard work to do the calculations, and also it might be not so clear or intuitive what happens if we change them just from the solutions. So it would be nice to see how does this solution change if I change one of the parameters. And yes, well, one way of thinking of this, which is not so much used here, but just to make the connection, is that, well, you can think this as a function of many different variables and to see how the function changes when the variables changes, these are the partial derivatives. Okay. So since the font is getting a bit smaller, I will again adjust a little bit the windows here so we can see better, like this. So with a function like this, obviously there are these three types of partial derivatives that are related. So first we could look how the optimum changes if the objective function c changes in its parameter, say, or component ci. The same thing we could ask for if the technology matrix changes in this aj component. Or we can look at the changes in the available resources, or the right hand sides here, which I usually interpret them as resources. In sometimes it's a reasonable thing to do. Sometimes it's maybe not completely reasonable to interpret them as resources. It depends on the problem, of course. Okay. Now this would be the natural thing to do, and yes, quite often this is not exactly what is done with the LP business. So indeed, these first two changes, those are changes in the objective function or the changes in the technology coefficients, they don't have standard names or concept. They are not standard concepts in the linear programming, and we shall actually not consider them. The reason is actually rather technical. The thing is that they are very difficult to calculate. It's not that we wouldn't be interested in them. We would be indeed very interested in them, but in practice it's not so easy to get them. Then on the other hand, these last changes, so the changes in the available resources. So suppose we want to know how the objective function, so say the daily revenue in the Muad'Dib's problem, how does it change if we have, say, one additional resource bj. So for example, one additional unit of spice melange. And these actually are something that are easily to come by. GLBK will give us them immediately if we ask them. These are called shadow prices. And these shadow prices, they are usually denoted by, well, lambdas or mu's or pi's. In my previous notes, if I remember correctly, I denoted them by pi's. Now I've decided in these notes to denote them by lambdas. So lambda j is the partial derivative of the optimal solution with respect to the resource bj. And we will have soon a section where we consider them more closely. Then there is another set of sensitivity parameters that are called reduced costs. Okay, so the shadow prices, they were related here to this b. So the reduced costs are actually related to the objective function c here. So one might think that they are then these partial derivatives of the optimum with respect to ci. And this is an easy mistake to make, I suppose, since I made it. But they are not actually that. They are something slightly more, I don't know, maybe complicated, maybe nebulous. So we will look at them later in a subsection or section of this chapter. At this point, I just say that they are somehow related also not only to z star, but the decision variables. There are what the decision variables are. And if we are producing, so think about the more deep problem again. So these xi's are the cakes, and if we are producing one cake, some cake x1 say, that was, if I remember correctly, the Atreides cake, then the reduced cost related to that is 0. So that's reduced cost in that case is not interesting to us. But if we do not produce it, so xi star, so star mean at the optimum, if that equals 0, then the reduced cost is something else than 0 usually, and then we are interested in it. So in that sense, the reduced costs are also related to the optimal decision, not only this optimal value, which here I just say that, okay, we can think of this LP here as a function of these parameters, but what are the outputs? It's not only the Z star, that it's the optimal revenue for the product mix problem, or the objective value for the Z here, optimal, but also the optimal decisions x's or x stars, star denoting the optimum. And yeah, in that sense, the reduced costs are closely related to actually the decision, really. Okay, now you might think that maybe they are the partial derivatives with respect to ci of this x star, and then the question is, what does this even mean, since this is now a vector? What is the, so it's a vector valued function. Okay, you can make sense of this partial derivative. It will actually, then it should turn out to be a matrix, but they are not these either. So they are something slightly different, and it's actually unfortunate that the definition is even somewhat complicated, but how to use the reduced costs will be explained later. Okay, that was the short introduction. I still want to emphasize that nothing happened in this introduction. We just vaguely introduced the idea and what the concepts are more or less like, and then in the further videos we will go into actual detail and give a proper definitions and see how they work. See you in further video lectures. Bye.